So it is a little confusing, right? But we just have to think about, I'm breaking bonds, I have to put energy in. When I make bonds, energy comes out. So this is the investment you have to make, and this is the payout that you get. So this is one of those Born-Haber cycle type diagrams. So enthalpy or energy going up as we go up the screen. So if we're reacting methane with chlorine, we need an overall chemical equation here. We have CH4 plus Cl2 making CH3Cl plus HCl. That's what we're doing here. So in order to make these two things out of this, I have to break one of these hydrogen-carbon bonds, and I have to break this chlorine-chlorine bond to pull those apart. So that's going to require energy. And then I can put the hydrogen with this chlorine, and I can put this chlorine on this piece over here, and when I form bonds, energy is released. And more energy is released than I had to put in to break the bonds. And so the overall enthalpy change is here. I put energy in to break bonds, energy is released. Releasing energy is negative to form bonds. Okay? This is an example of just looking at the bonds that are actually broken. We didn't do anything with the other 3 carbon-hydrogen bonds because they stayed there. So we often talk about energy being stored in chemical bonds. And there's not really a better way to briefly say it, but it's important to understand breaking a bond requires energy. It's not that you break the bond and it gives you energy. You have to put energy into it. An energy-rich compound can undergo a reaction in which weak bonds are broken and strong bonds are formed. Because it's when the bond forms that energy is released. Okay? It's the forming of the bond that releases energy. Okay, conceptual question. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energy bonds that break and form during the reaction? So, before we look at the choices, if it's highly exothermic, what does that mean about delta H? It's negative, right? Energy is being released. So let's look at the choices. The energy needed to break the required bonds is greater than the energy released when the new bonds form. Well, the breaking would be positive and energy released is negative. So if breaking is a bigger number than releasing, this is going to give me a positive delta H, right? That's going to be endothermic. So that can't be right. The energy needed to break the bonds is less than the energy released when the new bonds form. Would that give me negative delta H? Would that be a release of energy? Yeah, it would. And the last choice, the energy needed to break the required bonds is about the same as the energy released when the new bonds are formed. That doesn't match up with this being highly exothermic. This could be exothermic if the bond energy to break them is slightly less. It could be exothermic, but it's not going to be highly exothermic. Any questions? It's like business, investing money and getting a return. Right? So an exothermic reaction, you have to invest a little bit to break some of those bonds. But when the reaction occurs, you get that back with interest, and you get a big payout in an exothermic process. An endothermic process, you put a little bit of energy in there to make the bonds, and what gets released is less than what you put in, and so you end up losing. That happens too. Potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. Well, first we need a chemical equation. So they told us what the formula for methanol is. And it's combusting. What's the other reactant? Oxygen. And what are the products? H2O and CO2. When you burn something that's got carbon and hydrogen, or carbon and hydrogen and oxygen, the products are always CO2 and H2O. Just, they are. So then we have to balance this. So I have one carbon and one carbon, that's all nice. And I have 3 plus 1, 4 hydrogens here, and I only have 2 there. So I'll put a 2 in front of the water. And then I've got 2, and 2 is 4. I've got 4 oxygens over here, and I've got 2 plus 1. Dang. This is the odd even problem, so let's just double things. So I'm going to double this, and I'm going to double this, and I'm going to double this. And doing that keeps my hydrogens and my carbons balanced. And now when I look at the oxygens, I have 2 times 2 is 4 plus 4. So there's 4 oxygens there, and there's 4 oxygens here, so I need 8. Over here, I've got 2 oxygens there, and so I need 6 in here, right, to make 8. So this must be a 3. Okay? That's a review of chapter 4. Okay. So we could look at, some of these bonds might stay intact, and so we could just leave those alone. Personally, I think it's way too much thinking. I'd rather just break everything and make everything, right? So let's look at how much energy it would require to break all these bonds. Well, we need to know what kinds of bonds we have. So methanol, we can write the Lewis structure, and we're going to come up with that. And oxygen is going to look like that with a double bond. We just talked about how to do that, so I'm not going to do all of that in detail. So, in 1 mole of this compound, we have to figure out, well, how many moles of each of these kinds of bonds? Well, first of all, what kinds of bonds do we have there? Well, there's carbon-hydrogen bonds, and there's a carbon-oxygen bond, and there's an oxygen-hydrogen bond. We have 3 carbon-hydrogen bonds. 1, 2, 3. And then there's a carbon-oxygen and an oxygen-hydrogen. Everybody okay with that? So in this molecule, I have 3 carbon-hydrogen bonds, 1 here, and here, and there. So I wrote 3 carbon-hydrogen bonds. And I have a carbon-oxygen single bond, so I wrote that over here, and an oxygen-hydrogen single bond. So in 1 mole, I would have 3 moles of this bond and 1 and 1. But how many moles do I have here? 2. So I'm going to have 6 moles of that bond and 2 moles of this bond and 2 moles of that bond. Okay? In the oxygen, I have 1 oxygen-oxygen double bond. But I have 3 moles of that, so that's going to be multiplied by 3. You with me? So we can go look up these bond energies. So carbon-hydrogen, carbon-oxygen single, oxygen-oxygen, oh, I forgot the oxygen-hydrogen, oxygen-oxygen double bond. So carbon-oxygen single bond is 360. That's this guy right here. And carbon hydrogen is 414. And oxygen hydrogen is 464. And oxygen double bond is 498. And then while I'm here, I'm going to write down some of the other things that I know I'm going to need. Yeah, that's it. Carbon oxygen double bond in CO2. So you could look at this as like maybe, I don't know, you're trying to start a small business, you're making some craft thing, right? And here we're going out and we're finding out, well, I need this many of this object and this many of this, and then, you know, there's prices and there's going to be a cost for making this object, right? And then you look on Etsy and see if you can sell it and what you could sell it for. And sometimes you can't even sell it for the cost of the materials, right? So over here, I need to break 6 carbon-hydrogen bonds. And I looked up the energy for that, and it's 414 per mole, kilojoules per mole. So I've got 6 moles of that times 414 kilojoules. And then I need to break 2 carbon-oxygen bonds, or 2 moles of them. And so that's 360 kilojoules. That's just kind of ugly there. 2 oxygen-hydrogen bonds, 2 moles, 464, and 3 moles of oxygen double bonds.